Hello there, my dear friend, and welcome to Desire Sleep Stories. It is wonderful to have you here with me tonight as we prepare for a night of deep, restorative sleep. Whatever the day has brought, it is time now to let it all go. Settle into your bed, pull the covers over you if it feels right, and allow your body to find that perfect position of comfort. Close your eyes if they are not already, or soften your gaze. Take a slow breath in through your nose, hold it gently for a moment, and exhale slowly through your mouth, releasing any tightness in your shoulders, your neck, your jaw. With every breath, feel yourself sinking deeper into relaxation, your mind becoming calm and open, ready for our journey. Tonight, we are going to take a slow, peaceful voyage together through one of the most beautiful cycles in the universe, the life and death of stars. This is not a story of rushing or excitement, but a gentle exploration of how these luminous beings are born in quiet clouds, live their long or short lives, shining steadily, and eventually transform in ways that enrich the cosmos itself. As you listen, let the words wash over you like a soft cosmic breeze. You can drift in and out of awareness as much as you like. The stars have been there for billions of years, and their story unfolds over immense timescales that invite us to slow down and simply be. Let us begin far out in the depths of space, in regions where the universe is at its most serene and mysterious. Picture, if you will, immense molecular clouds, vast collections of gas and dust that stretch for hundreds of light years across the emptiness. These clouds are incredibly cold, with temperatures hovering around 10 to 20 degrees above absolute zero. In this frigid environment, the particles of hydrogen and helium, along with tiny grains of dust, drift ever so slowly. Gravity, that gentle but persistent force, begins to work its magic over countless millennia. Small density fluctuations within the cloud start to pull material inward. As clumps form, they grow denser, and the process accelerates in a quiet, inexorable way. Imagine yourself floating calmly within one such cloud, like the famous Orion Nebula, located about 1,344 light-years from us. The gas swirls in slow motions, illuminated faintly by distant light. Over time, these clumps collapse under their own weight. Friction and compression cause the core to heat up gradually. When the temperature in the center reaches thousands of degrees, a protostar begins to form, a baby star still gathering material from its surroundings. It may have an accretion disk around it, where material spirals in slowly, and sometimes powerful jets shoot out from the poles, carving through the cloud in elegant streams. This phase can last hundreds of thousands, or even millions of years for some stars. The protostar is not yet fusing elements in its core, it is still contracting and warming. As you relax deeper, consider how this birth process happens in clusters. Many stars are born together in stellar nurseries, like the pillars of creation in the Eagle Nebula. These towering columns of gas and dust stand several light-years tall. Ultraviolet light from nearby hot stars slowly erodes the pillars, while new stars hide within their dense cores, known as evaporating gaseous globules. The process is patient and methodical, governed by the balance of gravity and pressure. Eventually, when the core temperature climbs to about 15 million degrees Kelvin for a star like our Sun, nuclear fusion ignites. Hydrogen begins to fuse into helium through the proton-proton chain, a series of gentle nuclear reactions that release energy in the form of light and heat, powering the star for its long main sequence life. This fusion is the heart of a star's life. For stars of about the Sun's mass, the proton-proton chain dominates. Two protons come together, one transforms into a neutron, releasing a positron and neutrino, forming deuterium. Then more steps slowly build helium. The energy produced pushes outward, balancing the inward pull of gravity. It is a delicate, stable equilibrium that can last for billions of years. Our own Sun has been in this phase for about 4.6 billion years. and has roughly another 5 billion to go before its hydrogen fuel in the core depletes. And so the star settles into its main sequence life, shining steadily. On what astronomers call the Hertzsprung Russell diagram, a map of star properties, it occupies a position based on its mass and temperature. Lower mass stars are cooler and dimmer on the right, hotter massive ones brighter and bluer on the left. This steady phase is where most stars spend the majority of their existence, quietly converting hydrogen to helium while radiating the energy that eventually allows planets like Earth to exist and life to flourish. As your breathing slows even more, let these images of distant star birth fill your mind with a sense of wonder and peace. The universe is vast and patient, and we are part of its ongoing story. Now, let us linger a little longer in these nurseries before we move forward along our slow journey. To understand the very beginning of a star's life, we drift even further back into the interstellar medium itself, the vast spaces between the stars that fill our galaxy with sparse but essential material. This medium is not empty. It contains about 1 atom per cubic centimeter on average, mostly hydrogen and helium left over from the early universe, mixed with traces of heavier elements from previous generations of stars. Over time, these atoms and molecules gather into giant molecular clouds, some of the largest structures in the galaxy, spanning up to several hundred light years and containing enough mass to form tens of thousands of stars. These clouds are dark and cold because the dust grains within them absorb and scatter light, shielding the interior from the harsh radiation of distant stars. Temperatures inside remain steady at those 10 to 20 degrees above absolute zero we mentioned. Gravity, acting over millions of years, causes slight overdensities to collapse. The process is known as Jeans instability, where the cloud's own gravity overcomes the internal pressure that tries to hold it apart. As a clump collapses, it fragments into smaller pieces, each destined to become a star, or perhaps a group of stars. Consider the Orion Nebula once more. Visible even to the naked eye as a fuzzy patch in the sword of the constellation Orion, it is one of the closest and most active star-forming regions. At its heart lies the trapezium, a cluster of 4 bright young stars whose intense light illuminates the surrounding gas, causing it to glow in beautiful shades of pink and green. The hydrogen gas emits that characteristic red-pink hue when energized, while oxygen and other elements add subtle blues and greens. Embedded within the nebula are hundreds of protostars, some still hidden behind thick veils of dust, detectable only in infrared light. Space telescopes have revealed disks of material around many of these young stars, disks that may one day form planets. The collapse of a typical dense core within such a cloud takes about 100,000 to a few million years. As the material falls inward, it heats up through gravitational energy conversion. The protostar at the center grows hotter and denser. Jets of material called Herbig-Haro objects, when they collide with surrounding gas, stream out at hundreds of kilometers per second. But even these energetic outflows happen on timescales that feel slow and deliberate when viewed across cosmic distances. The jets carve cavities and help regulate the star's growth by removing excess angular momentum. Different clouds have different compositions and densities, leading to different kinds of star formation. Some clouds are triggered to collapse by the shock waves from nearby supernovae or by the passage of spiral arms in the galaxy. Others form spontaneously. In all cases, the birth is a gradual process of gathering and compressing, never hurried. Once the protostar reaches a point where its core temperature allows fusion to begin, it enters a brief phase called the T-Tauri stage for Sun-like stars, where it is still accreting material, but starting to shine with its own light. This phase lasts a few million years at most. As we continue to drift through these nurseries in our minds, notice how the newly formed stars begin to clear away the gas around them. Their radiation and winds push the remaining material outward, sometimes revealing the young cluster in all its glory. The Pleiades star cluster, visible on clear nights, is an example of a young group that has recently emerged from its birth cloud. Its stars are still surrounded by faint reflection nebulae, blue light scattered by remaining dust. Over tens of millions of years, the cluster will disperse, but for now it stands as a testament to the gentle, ongoing process of stellar birth. The interstellar medium is enriched slowly by previous generations. Every heavy element we see today, from carbon to iron and beyond, came from earlier stars that lived and died. Without those previous cycles, new stars could not form planets with rocky surfaces or the complex chemistry needed for life. Yet, this enrichment happens quietly, one atom at a time, over billions of years. As you breathe slowly now, let the vast patience of these nurseries soothe you. There is no rush in the cosmos. Everything unfolds in its own time, just as your body is finding deeper rest with each passing moment. We could spend hours describing the variety of star-forming regions across the galaxy. The Carina Nebula, for instance, lies about 7,500 light-years away and contains some of the most massive stars known, whose fierce radiation sculpts dramatic landscapes of gas. The Rosette Nebula, shaped like a flower, spans about 100 light-years and harbors dozens of young stars. Each one offers its own quiet beauty, its own slow story of creation. But for our journey, we will follow a few representative paths, allowing the details to unfold gently so your mind can wander freely among them. Once the protostar has gathered most of its mass and fusion has begun in earnest, the star settles into its main sequence phase. This is the longest and most stable part of its life. For a star like our Sun, this phase lasts about 10 billion years in total. The energy generated in the core through fusion travels outward, first by radiation in the inner layers and then by convection in the outer layers, eventually reaching the surface as visible light and heat. The surface temperature of the Sun is about 5,500 degrees Celsius, giving it its familiar yellow-white glow. Its diameter is about 865,000 miles, large enough that more than 1 million Earths could fit inside. The proton-proton chain we touched on earlier is a wonderfully efficient yet gentle process. It requires high temperatures and pressures only found deep in the core, where the density is about 150 times that of water. Every second, the Sun converts about 400 million tons of hydrogen into helium, but because of the famous mass-energy equivalence, only a tiny fraction of that mass is turned into energy. The rest becomes helium. This tiny conversion rate is enough to keep the Sun shining steadily for those billions of years. Stars of different masses live at different rates. More massive stars burn their fuel faster because their cores are hotter and denser. A star 20 times the mass of the Sun might spend only a few million years on the main sequence, while a star half the Sun's mass could shine for tens of billions of years. On the heart-sprung Russell diagram, these stars line up in a diagonal band. The hottest, most massive ones are blue and luminous at the top left. Cooler, less massive red dwarfs sit at the bottom right. Our Sun is a middle-of-the-road, yellow dwarf, spectral type G2. During this main sequence time, the star maintains perfect balance. Gravity pulls inward, fusion pressure pushes outward. Any slight imbalance is corrected naturally. If the core gets a little hotter, fusion increases, pushing the outer layers out until balance returns. This self-regulating mechanism keeps stars stable for eons. We know this from observing thousands of stars at various stages, from spectroscopy that reveals their composition and temperature, and from models that match what we see in clusters of different ages. Let your mind drift now to a star similar to our Sun. It shines quietly, providing steady light. Around it, planets may form from the leftover disk of material. In our own solar system, that disk gave us Earth and the other worlds. The light from such stars travels across space, taking years or centuries to reach us. When we look at the night sky, we see some stars as they were long ago. The light from the nearest star, Proxima Centauri, took over 4 years to arrive. Yet, in cosmic terms, that is almost nothing. The main sequence phase is where stars spend most of their lives, quietly contributing to the galaxy's glow. For lower mass stars, the fusion is simple. For more massive ones, the carbon-nitrogen-oxygen cycle takes over once the core temperature exceeds about 15 million degrees Kelvin. This cycle uses carbon as a catalyst to fuse hydrogen more efficiently. It allows the star to shine brighter and hotter. Massive stars appear blue or white to our eyes. Their surfaces can reach 30,000 degrees or more. Their winds are stronger, blowing material into space at thousands of kilometers per second, slowly shedding mass even during the main sequence. As we pause here in the steady light phase, notice how peaceful it feels. A star in this stage radiates calmly for ages. Its light supports the possibility of life on orbiting worlds. The energy output is constant enough that planets can maintain stable climates over geological time. Our Sun has done exactly that for Earth. The slight changes over billions of years have been gradual, allowing evolution to proceed at its own pace. This steadiness is a gift of the main sequence, one we can feel in the warmth of sunlight on a quiet day. For our slow journey, we will follow 2 main paths, one for sun-like stars and one for the more massive ones. Both paths are filled with the same quiet dignity, the same patient unfolding of physical laws. As your body continues to relax, let these steady lights fill your inner vision with a soft, golden glow. There is time enough for everything in the universe. There is time for you to drift towards sleep as we continue. Most stars spend 90% of their lifetimes on the main sequence, shining with the light from hydrogen fusion. For a sun-like star, that means about 9 billion years of steady output. During this time, the core slowly builds up helium ash. The helium does not fuse yet because it requires even higher temperatures, about 100 million degrees Kelvin. So the core contracts very gradually as hydrogen is depleted and the outer layers expand slightly to compensate. These changes are minuscule over human lifetimes, but accumulate over billions of years. Astronomers study this phase by looking at star clusters. Open clusters like the Hyades contain stars of similar age, allowing us to see how they evolve together. Globular clusters, ancient and dense, show us what happens to stars over 12 billion years or more. In these clusters, we see the main sequence turn-off point, where stars of a certain mass have left the main sequence while lower mass ones remain. This tells us the age of the cluster precisely. The turning point comes when the hydrogen in the core is finally exhausted. For the Sun, this will happen in about 5 billion years. At that moment, the core, now mostly helium, begins to contract under gravity. The temperature rises and hydrogen fusion starts in a shell around the inert helium core. This shell burning causes the outer layers to expand dramatically. The star leaves the main sequence and becomes a subgiant, then a red giant. The surface cools as it expands, turning orange-red, while the luminosity increases hundreds of times. The radius can grow to more than 100 times its original size. This expansion happens slowly over hundreds of millions of years. For our Sun, the red giant phase will see it swell until its surface reaches roughly the orbit of Mercury or even Venus. The inner planets may be engulfed. Earth will likely have become too hot long before. Its oceans evaporated billions of years earlier as the Sun's luminosity gradually increased even on the main sequence. Yet these changes unfold over timescales so vast that they feel almost timeless. Inside the red giant, the helium core continues to contract until it reaches about 100 million degrees. Then, helium fusion ignites in what is called the helium flash for low-mass stars. This is a brief burst of energy, but it quickly settles into steady helium burning, producing carbon and oxygen. The star may climb the red giant branch multiple times, with thermal pulses causing it to brighten and dim in cycles lasting tens of thousands of years. During these pulses, the star loses mass through strong stellar winds. Material is gently blown off into space, forming beautiful shells. This mass loss is crucial because it prevents the star from becoming too massive for its final stages. The lost material enriches the interstellar medium with carbon, nitrogen, and oxygen, atoms that will one day form new clouds and new stars. For stars with initial masses up to about 8 times that of the Sun, the path after the red giant is relatively gentle. After helium is exhausted in the core, the star again expands, becoming an asymptotic giant branch star. Here, fusion occurs in 2 shells, hydrogen and helium. Thermal pulses become more pronounced. The star can lose up to 70% of its mass in these winds. Eventually, the outer layers are shed completely, forming a planetary nebula. These are among the most beautiful objects in the sky. The ring nebula in Lyra looks like a smoke ring through a telescope, about 1 light-year across, expanding at about 20 kilometers per second. The Helix Nebula appears like a giant eye, with intricate cometary knots of gas. The Cat's Eye Nebula shows complex structures shaped by magnetic fields and stellar winds. These nebulae glow for about 10,000 to 50,000 years as the ultraviolet light from the exposed core ionizes the gas. What remains is the core, now a white dwarf. A white dwarf is about the size of Earth but contains roughly the mass of the Sun. Its density is enormous. A teaspoonful would weigh several tons on Earth. The electrons in its atoms are packed so tightly that quantum pressure, called electron degeneracy pressure, supports it against gravity. No fusion occurs anymore. The white dwarf simply cools over trillions of years, eventually becoming a black dwarf, though the universe is not yet old enough for any to have reached that stage. The Chandrasekhar limit tells us that white dwarfs cannot exceed about 1.4 solar masses. If they do, through accretion in a binary system, they can trigger a different kind of explosion. But for single stars like the Sun, the white dwarf is the peaceful end. Sirius B, the companion to the bright star Sirius, is a well-studied white dwarf about 8.6 light-years away. It is roughly Earth-sized, but packs the Sun's mass into that tiny volume. For our Sun, this final stage will be quiet. The white dwarf will shine faintly with residual heat for billions of years, slowly fading. The material it ejected will mix back into the interstellar medium, waiting patiently for the next generation of stars. This cycle is gentle and inevitable, a natural part of the universe's rhythm. Now let us turn our attention to the more massive stars, those born with more than 8 solar masses. Their lives are shorter, but equally important to the cosmic story. A star of 20 solar masses might spend only 10 million years on the main sequence. It burns through its fuel rapidly, shining hundreds of thousands of times brighter than the Sun. Its surface is hot and blue. Examples include Rigel in Orion or Deneb in Cygnus. These stars evolve quickly after the main sequence. They become red supergiants, expanding to hundreds or even 1,000 times the Sun's radius. Betelgeuse, the red shoulder of Orion, is a classic example. It is about 600 light-years away and varies in brightness over time. Recent observations show it has a companion and has dimmed at times, but its future remains clear. When its core fusion runs out, it will collapse. For high-mass stars, the core progresses through stages of fusion: helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. Each stage lasts shorter than the last. The iron core cannot fuse further because iron fusion absorbs energy rather than releasing it. When the iron core reaches about 1.4 solar masses, electron degeneracy pressure fails and the core collapses in seconds. This collapse triggers a core collapse supernova. The outer layers fall inward, bounce off the newly formed neutron core, and explode outward. The explosion releases enormous energy, mostly in neutrinos, but enough light to outshine an entire galaxy for weeks. The Crab Nebula is the remnant of a supernova seen in the year 1054. It lies about 6,500 light-years away and contains a pulsar, a rapidly spinning neutron star, at its center. Neutron stars are incredible objects. They are about 12 miles across, yet contain 1.4 to 2 solar masses. A teaspoon would weigh billions of tons. They spin rapidly, some hundreds of times per second, and emit beams of radiation like lighthouses. If the core is more than about 3 solar masses, it collapses further into a black hole where gravity is so strong that not even light can escape. Type 2 supernovae from single massive stars are one kind. Type 1a come from white dwarfs in binary systems that accrete too much mass and explode. Both kinds scatter heavy elements into space. Gold, uranium, and many others are created in these events through rapid neutron capture, the R process. The remnants of these explosions are beautiful in their own quiet way. Supernova remnants, like Cassiopeia, show expanding shells of gas glowing in X-rays and radio waves. The filaments are rich in oxygen, sulfur, and other elements. These remnants expand for thousands of years, eventually merging with the interstellar medium. The heavy elements created in stars and supernovae enrich future molecular clouds. Every atom in your body, heavier than hydrogen and helium, was forged in some ancient star. The carbon in your cells, the oxygen you breathe, the iron in your blood, all came from these processes. This connection ties us to the stars in the most fundamental way. New stars form from this enriched material. The cycle continues. Galaxies like the Milky Way have been recycling material for 13 billion years. Star formation rates vary, but the process is ongoing and peaceful. In the Large Magellanic Cloud, we see active regions like the Tarantula Nebula, where massive stars are born and die, feeding the next generation. Black holes, once formed, can grow by accreting material or merging. They influence their surroundings gently over time, shaping galaxies through feedback. Neutron stars can be part of binary systems, producing X-ray sources or gravitational waves when they merge. The universe is a vast recycling system. Nothing is wasted. Every death feeds new birth. This endless loop brings a profound sense of calm when we reflect on it. Returning to our sun, its future is written in the same gentle script. In about 5 billion years, it will leave the main sequence. It will expand into a red giant, possibly reaching the orbit of Earth. Its outer layers will be shed, forming a planetary nebula. The remaining white dwarf will cool slowly. The planets that survive will orbit this faint ember. The material ejected will join the interstellar medium, perhaps one day forming new stars and planets. This distant tomorrow is nothing to fear. It is part of the natural rhythm. Our sun has given life to Earth for 4.6 billion years already and will continue to do so for billions more. When the time comes, the cycle will carry on. As our slow journey through the life and death of stars draws to a close, let these images settle gently in your mind. The birth in quiet clouds, the steady shine for eons, the transformations, the remnants, and the new beginnings all weave together in a cosmic dance that has no end. You are part of it. Every breath you take contains atoms from long ago stars. Let these thoughts flow through you now. The journey has been long and gentle, covering birth, life, transformation, and renewal. Every detail we explored shows the same underlying peace. Gravity pulls softly. Fusion glows steadily. Expansion happens gradually. Ejection is calm. Cooling is slow. New clouds form patiently. You have traveled with the stars tonight. Your mind has wandered among nebulae, giants, remnants, and cycles. As you feel yourself drifting deeper into sleep, know that the universe continues its patient work. Stars are being born right now, living their lives and returning their gifts to the cosmos. There is peace in this knowledge. There is peace in the vastness. The universe holds you gently, just as it holds the stars. Let go completely now. Allow sleep to come softly, carrying you into restful dreams. Good night, my friend. Sleep well, surrounded by the gentle light of stars past, present, and future.